Welcome everyone to this month's AQFP seminar. Pawel Duch got his PhD in 2017 from Krakow University with his supervisor Herdegen. He worked on a couple of things already, among which are massless fields in perturbative quantum field theory, a notoriously difficult subject. He was at Leipzig in Felix Otto's and my group, joint postdoc between 2019 and 22, where he also turned his attention to stochastic PDEs, the topic of today's talk. He's in Poznan University at the moment. Thank you for coming, Pawel. It's yours now.
Thank you very much for this kind introduction, and thanks for the invitation to speak at this seminar. So the title of my talk is Weak Universality and Singular Stochastic PDEs. As you may know, the large-scale behavior of many physical systems interacting with random environments can be described in terms of stochastic PDEs. The large-scale behavior often exhibits the so-called universality. The macroscopic scaling limit of many different microscopic systems is described by the same family of stochastic partial differential equations, depending only on a few parameters. In this talk, I would like to present a universality type result for a class of stochastic PDEs with fractional Laplacian, additive smooth noise term, and polynomial non-linearity. I proved that the macroscopic scaling limits of solutions of equations of this form are described by a finite dimensional family of singular SPDEs driven by the white noise. The result extends previous universality results for models whose large-scale behavior is governed by the KPZ equation or the dynamical 543 model. A nice feature about this result is that it applies to situations when the equation obtained in the scaling limit is close to critical. The result covers the full subcritical, that is super renormalizable regime. I use the framework of continuous normalization group, and my approach is inspired by the approach to singular SPDEs developed earlier by Kupiainen. A novel element of my approach that allows to treat systematically a very large class of equations is the application of a renormalization group flow equation. The flow equation plays analogous role to the Polchinski equation in quantum field theory. I will start with a few examples of singular SPDEs, and I will recall what it means to solve a singular SPDE. Then I will introduce the notion of weak universality for stochastic PDEs. Next, I will formulate the main result of this talk, which is a universality result for a class of stochastic PDEs with fractional Laplacian. Finally, I will give you some elements of the proof, which is based on the renormalization group flow equation. Okay, in the talk, I will consider parabolic SPDEs posed in space-time of dimension d+1, the spatial domain will be either Rd or d-dimensional torus. The first example of a stochastic PDE that I would like to give you is the stochastic heat equation, which is a linear and regular equation. The source term, psi, appearing on the right-hand side of this equation is the so-called white noise, which is a random and irregular object. So you can think of the white noise as a randomness that is completely uncorrelated in both space and time. More precisely, the white noise is the unique Gaussian random variable valued in the space of Schwartz distributions, such that its mean vanishes and its covariance coincides with the Dirac delta. Let me also recall two non-linear SPDEs, the KPZ equation and the dynamical phi-4D model. Both equations are singular. The expected regularity of the solutions of these equations are not sufficient to make sense of the non-linear terms that appear in these equations. So, for example, in the case of dynamical phi-4D model, in dimensions greater or equal to 2, the solution is not expected to be a function, but only a distribution. Since multiplication of distributions is not a well-defined operation, the cubic term is ill-defined. Okay, in order to make sense of a singular SPDE, one usually first introduces a certain regularization. To this end, one can, for example, replace the white noise psi by some smooth noise psi kappa that converges to psi as the UV cut of kappa goes to 0. Next, one renormalizes the equation. So, for example, in the case of the dynamical phi-4 model, a mass counter term is needed. Finally, one proves that for appropriate choices of the counter terms, the limit kappa goes to 0 of the solution of the regularized and renormalized equation exists. By now, this procedure is well known to work in the case of subcritical SPDEs, such as dynamical phi-4 model in dimensions 2 or 3, or the KPZ equation in one spatial dimension. The renormalization problem is very difficult in the case of models close to critical. The framework that can be used to solve such equations was developed only recently. The main result of this talk provides in particular a well-posedness result for a class of singular SPDEs in a full subcritical regime. However, the result goes beyond the solution theory. I proved the so-called weak universality. So let me introduce to you the notion of weak universality in the context of stochastic PDEs. So this part of the talk will be very informal. I am going to study two models. The first model is the model of a polymer chain in a random environment. So you can think, for example, of a DNA molecule in a liquid. We model the polymer as a chain of beads which are connected by springs. The position of the if bead at time t is denoted by psi at t and I. For simplicity, we assume that the beads can only move in one direction. So psi takes real values. There are three forces exerted on each of the beads. So there are two forces exerted by the springs, which are depicted in orange and green. And there is also the force exerted by the environment depicted in magenta. The forces exerted by the springs are proportional to their elongations. These forces are responsible for smoothing of the function psi. The forces exerted by the environment depicted in magenta are random, and we assume that the random forces acting on different beats are identically distributed and independent. Moreover, we suppose that there are only short-range correlations in time. Okay, here I copied the equation from the previous slide. I call this equation the microscopic equation. Observe that the sum of the first two brackets coincides with the discrete Laplacian of psi on the unit lattice. So I can rewrite the equation in this form. We are interested in a large-scale macroscopic behavior of the system. To this end, we consider the following scaling transformation. The scale parameter kappa takes values between 0 and 1. So this scaling transformation corresponds to zooming out. And ultimately, we are interested in the limit kappa goes to 0. The scaling transformation is chosen in such a way that it plays nicely with the parabolic differential operator partial t minus Laplacian. The rescaled process, denoted by phi kappa, satisfies the following macroscopic equation involving the rescaled noise psi kappa and the discrete Laplacian on a lattice with spacings square root of kappa. The prefactors in the scale transformation are chosen in such a way that the covariance of the rescaled noise converges to the Dirac delta. Actually, under some natural assumptions about the random forcing zeta, the rescaled forcing psi kappa converges in law to the white noise psi as kappa goes to 0. Because of that, the macroscopic scaling limit, defined as the limit kappa goes to 0 of the rescaled process phi kappa, satisfies the stochastic heat equation driven by the white noise. Okay, now let me consider a more complicated model, the so-called interface fluctuation model. So now we are interested in the evolution of the height function of a certain one-dimensional interface separating two phases. We assume that the height function denoted by psi satisfies the following microscopic SPDE. So we assume that there is some smoothing mechanism that is modeled by the Laplacian term. The influence by the environment is modeled by some random forcing zeta. And moreover, we suppose that there may be some non-linear term that depends on psi and its gradient. We assume that the forcing zeta is smooth, stationary, centered, admits moments of all orders, and moreover has only short-range correlations. We also impose certain symmetries. So the evolution of the system should not depend on the choice of the reference height. Because of that, the system should be invariant under the transformation psi goes to psi plus some constant independent of x. Moreover, the equation should be invariant under spatial reflection. The third sign flip symmetry is optional, and this symmetry is only expected in models in which no of the phases dominates the other. Okay, so if the first symmetry is satisfied, then the nonlinearity does not depend on psi, but only on its gradient. The second symmetry implies that the nonlinearity is an even function of the gradient. And it turns out that all three symmetries are implemented only if the nonlinearity vanishes. Here I gave you a natural example of the nonlinearity in the case of a model in which the interface tends to grow in directions perpendicular to local slope. Note that this choice of the nonlinearity obviously breaks the third symmetry. It turns out that the macroscopic scaling limit of a solution of the microscopic equation depends on the symmetries of the system. So if the system is invariant under all three symmetries, then the large-scale behavior is governed by the so-called Edwards-Wilkinson fixed point, which is described by the stochastic heat equation. So in particular, the scaling limit is Gaussian. On the other hand, if the third symmetry is broken, then the macroscopic scaling limit is described by the so-called KPZ fixed point. So this is some non-Gaussian Markov process whose characterization is unfortunately quite complicated. In particular, the KPZ fixed point does not satisfy any known stochastic PDE. It does not satisfy the KPZ equation, which is not even scale invariant. In order to understand how the KPZ equation arises, let us study in more detail the evolution of interface fluctuation models under the zooming out or rescaling transformation. So in this heuristic diagram, I depicted a certain two-dimensional subspace in the space of all possible microscopic equations. So the space is clearly infinite dimensional. So different points in this diagram depict different microscopic equations. Lines indicate the flow of models under the zooming out transformation. There are two fixed points of the flow, the Edwards-Wilkinson fixed point, which is Gaussian, and a certain non-Gaussian KPZ fixed point. The blue submanifold is the so-called stable manifold of the Gaussian fixed point. It consists of all models which flow towards the Gaussian fixed point under the zooming out operation. So such models respect all three symmetries, and in particular are described by microscopic equations with no linearity. The one-dimensional submanifold depicted in red, connecting the fixed points, is the so-called unstable manifold of the Gaussian fixed point. So the red submanifold consists of all points which can be obtained by rescaling a model that is an infinitesimal perturbation of the Gaussian fixed point. I claim that the KPZ equation describes points on the red manifold. Such points cannot be obtained as a scaling limit of a fixed model. However, one can obtain points on this manifold as a scaling limit of scale-dependent models. So we are going to consider a certain family of microscopic models corresponding to this class of microscopic PDEs, and we are assuming that these models depend on the scale parameter kappa, and as kappa goes to 0, the models approach the stable manifold of the Gaussian fixed point. So this means that in the limit kappa goes to 0, the non-linearity vanishes. So we are considering the so-called Ripley nonlinear regime. Moreover, we suppose that the coefficients of the non-linearity vanish polynomially as kappa goes to 0. Okay, so this is the class of microscopic models, and now we are applying the scale transformation with parameter kappa to such models, and we obtain models depicted in magenta. So it is clear that the rescaled models depicted in magenta will approach the red unstable manifold. It is, however, not obvious that the models depicted in magenta will converge to some point on the red manifold. Since this manifold is one-dimensional, the easiest way to ensure the convergence is to fix the projection of the rescaled models onto the one-dimensional unstable manifold. So as an aside, let me mention that in a very similar way, one can obtain or construct models of quantum field theory, such as, for example, the 543 model. So one can define such models as a macroscopic scaling limit of a scale-dependent family of microscopic models. There is only a slight complication, because in the context of 543 model, there are 3 fixed points, and the unstable manifold, which is in this picture depicted in red, is 2-dimensional, and consequently one has to fix 2 parameters, namely the effective mass and effective coupling constant. So coming back to the interface fluctuation models, here the unstable manifold is 1-dimensional, so we have to fix only 1 parameter. And because of that, the scaling limit will depend only on 1 real number. It turns out that the scaling limit is indeed described by the KPZ equation, and is universal in the sense that if we fixed the parameter lambda, then the scaling limit does not depend on the details of the microscopic model. So it is the same for different choices of the noise zeta and different choices of linearity n. So weak universality of interface growth models was established already some time ago under different assumptions about the noise and the nonlinearity. There are also similar results for phase coexistence models in 3 dimensions, whose large-scale behavior is governed by the dynamical 543 model. In this talk, I would like to present a result that is a generalization of these results to the case of models whose large-scale behavior is governed by SPDE with fractional Laplacians. So by tuning the order of the fractional Laplacian, I can study equations which are close to critical equations, like, for example, the dynamical phi-4 model in 4 dimensions. More precisely, I consider the following class of microscopic equations. So I assume that there is some term involving the fractional Laplacian of order sigma. There is an additive smooth noise term zeta, and there is also some polynomial non-linearity n. I suppose that this equation is posed in a compact domain. For concreteness in this talk, I will assume that this domain is a 4-dimensional torus of a size kappa to -1/sigma. So this is some big torus. I am considering the so-called I impose certain symmetries. So I assume that the equation is invariant under sign flip symmetry, and moreover, I also impose discrete rotations and reflections of the torus. So these conditions impose certain restrictions on the equation, and in particular, these conditions restrict the form of the nonlinearity. So here I gave you a possible example of the nonlinear term. I am studying the so-called weakly nonlinear regime, and I am assuming that the coefficients of the nonlinearity are bounded by some power of the scale parameter kappa. And then I am considering a rescaling that corresponds to the rescaling from the large torus of size kappa to -1/sigma to the unit torus. So I'm considering a certain zooming out operation. And the prefactors here in this rescaling transformation are chosen in such a way that the rescaled noise, denoted by psi kappa, converges to the white noise in the limit kappa goes to 0. So the rescaled process, denoted by phi kappa, satisfies the following macroscopic SPDE. This SPDE has a very similar form to the microscopic SPDE. The difference is that this equation is driven by the noise psi kappa that converges to the white noise. And moreover, the coefficients of the nonlinearity acquire certain powers of the scale parameter kappa. So recall that the coefficients of the nonlinearity in the microscopic equation from the previous slide were bounded by some power of the scale parameter kappa. On the other hand, the coefficients of the nonlinearity in the macroscopic SPDE behave differently depending on the type of the coefficient. So some of the coefficients are bounded by a positive power of kappa, and some coefficients are bounded by a negative power of kappa. The coefficients that are bounded by a negative power of kappa are called relevant. These coefficients potentially blow up in the limit kappa goes to 0. The coefficients bounded by a positive power of kappa are called irrelevant, and they vanish in the limit kappa goes to 0. Recall that the noise psi kappa converges to the white noise in the limit kappa goes to 0. This, together with the vanishing of the irrelevant coefficients, suggests that the macroscopic scaling limit satisfies the following SPDE involving the white noise psi and containing the nonlinearity with only two relevant terms, namely the linear term phi and the cubic term phi 0. So maybe perhaps I should stress that the fact that we have exactly two relevant terms is related to the choice of this constant delta. If the delta was bigger than this upper limit, then the cubic term would become irrelevant, and if delta was smaller than the lower bound, then the term Laplacian psi would become relevant. So under our assumption about delta, there are exactly two relevant terms, and this argument suggests that the scaling limit should be universal and should only depend on two parameters that appear in this equation. So this naive reasoning turns out to be correct in the sense that the scaling limit indeed exhibits universality. However, the proof of this fact is much more complicated, and this is related to the fact that this equation is very singular. Because of the irregular nature of the white noise, the solution is not expected to be a function, but only a distribution. Consequently, this cubic term appearing here is meaningless. Okay, so let me describe the main result of this talk. So I am studying a certain class of stochastic PDEs posed on a large four-dimensional torus. I assume that the noise zeta is smooth and has only short-range correlations. And I am assuming that the non-linearity is of polynomial type. I am considering the so-called weakly nonlinear regime, and I am assuming that coefficients of the non-linearity are bounded by a positive power of the scale parameter. We impose a certain restriction of the choice of the coefficients of the nonlinearity. Namely, we assume that the effective coupling constant and the effective mass and spatial scale 1 are fixed. And then the first part of the theorem says that the macroscopic scaling limit of the rescaled process living on the unit torus exists. So this reason, this result does not exclude the possibility of a finite time blowup. So I only prove existence of this limit in an open, possibly short time interval. The second part of the theorem is the universality result. So it says that for fixed values of the effective coupling constant and effective mass, the law of the scaling limit, denoted by phi 0, is independent of the choice of the noise zeta and polynomial n appearing in the microscopic equation. So as I said before, formally the macroscopic scaling limit solves the following SPDE. Observe that if sigma is equal to 2, then this SPDE coincides with the standard phi 4 model in 4 dimensions, which is critical. So this case is not covered by my analysis. However, my analysis covers the full subcritical regime corresponding to sigma strictly greater than 2. And in particular, the result from the previous slide implies the well-posedness of this class of SPDEs. So as I said, this is a singular SPDE. So to make sense of this equation, we have to regularize it. So we can replace the noise by, for example, a modification of the noise. And then this corollary says that there exists a choice of the mass counter term C kappa such that the limit kappa goes to 0 of the solution of the regularized equation exists. So it turns out that to prove this theorem, one can use to prove this corollary, one can use the theorem from the previous slide, and to this end, it is sufficient to find a microscopic equation that rescales to this equation under the zooming out operation. And we can simply take the microscopic noise to be the convolution of the white noise with some smooth kernel of compact support. And we can assume that the non-linearity contains only the linear and cubic terms. In the remaining part of the talk, I would like to describe some elements of the proof. So in the proof, I study the macroscopic equation, which is posed on the unit torus and is obtained by rescaling of the microscopic equation. So we are interested in proving that the solution of this equation, denoted by phi kappa, converges in the limit kappa goes to 0. We first rewrite this equation in the mild form. So ignoring for simplicity the initial condition, we get the following equation, where G is the inverse of the parabolic differential operator that appears in the macroscopic equation. So I call G the fractional fit kernel. Star denotes the spacetime convolution, and F kappa is the sum of the white noise and the non-linearity in the macroscopic equation. So this is just the right-hand side of the macroscopic equation. They call this object the force. Observe that in the limit kappa goes to 0, psi kappa converges to the white noise. Because of that, the scale parameter kappa plays the role of the ultraviolet cutoff. So in what follows, I will often call kappa the UV cutoff. Now I would like to introduce the so-called effective force, which is a certain generalization of the force. So the effective force is the fundamental object of the approach to singular SPDEs developed by Kupiainen. This object also plays a very important role in my approach. So let K mu be some smooth kernel of characteristic length scale mu. We are trivially splitting the solution of the macroscopic equation phi kappa into regular and irregular parts. The regular part involves a convolution of the solution with the kernel K mu. So this convolution, roughly speaking, corresponds to averaging over regions of size mu. Because of that, this regular part involves two UV cutoffs, mu and kappa, and for fixed positive values of mu, the regular part is smooth even in the limit kappa goes to 0. It turns out that the regular part satisfies the following equation, which are called the effective equation. This equation involves certain regularized propagator G mu and the effective force F kappa mu that satisfies this equation. The effective force depends on two parameters, kappa and mu, and is a non-local functional of a test function psi. Recall that kappa is the parameter that appears in the noise. As I said before, it plays the role of the UV cutoff. On the other hand, the parameter mu appears in the kernel G minus G mu. This kernel propagates only high frequencies, and because of that, in the effective force, the parameter mu plays the role of the infrared cutoff. Let me mention a few important properties of the effective force. So first, if the infrared cutoff mu vanishes, then this kernel vanishes, and consequently, the effective force coincides with the force, which is just the right-hand side of the macroscopic equation. I also claim that if the infrared cutoff is equal to t and psi vanishes, then then one can obtain in this way the solution of the macroscopic SPDE in a time interval from 0 to t. So this claim relies crucially on a clever choice of the kernel K mu that appeared from the previous slide. So summing up, the effective force with infrared cutoff equal to 0 is given, and in order to solve the equation, we have to construct the effective force with infrared cutoff equal to t. The fundamental idea of the renormalization group theory is to define the effective force in step by gradually increasing the infrared cutoff. And to this end, one can use this RG equation. So this equation is a generalization of this equation, and in this equation, the effective force with certain infrared cutoff eta is given, and one solves for the effective force with bigger infrared cutoff. So this equation played a central role in the approach to singular SPDEs developed by Kupiainen. I use a bit different approach, which allows to treat systematically a large class of equations in full subcritical regime. I define the effective force for all values of the infrared cutoff between 0 and 1 using a certain flow equation that can be derived from the RG equation from the previous slide. The flow equation is the equation for the derivative of the effective force with respect to the infrared cutoff. And I solve this equation with the initial condition that says that the effective force with vanishing infrared cutoff coincides with the force. In order to organize various expansions, I introduce a certain parameter lambda and assume that all terms of the non-linearity are at least of order lambda. In the end of the construction, one can set lambda equal to 1. To solve the flow equation, I make the following ansatz for the effective force. I assume that the effective force is a sum of terms of order lambda to some power I, and I suppose that each term in the sum over I is the sum of terms which are n-linear functionals of the test function psi. The distributions Fi n kappa mu that appear in the ansatz are called the effective force coefficients. The flow equation for the effective force implies a certain flow equation for the effective force coefficients, and using this this flow equation, one can construct the effective force coefficients recursively. So the recursion is in the order of ascending values of the index I and descending the order of the index m. At each step of the construction, we first express the derivative of the coefficient with respect to the infrared cutoff as a linear combination of the coefficients which have already been constructed. So in this step, we simply use the flow equation. Next, the coefficient itself can be obtained by integrating its derivative. Recall that the solution of the macroscopic equation, denoted by phi kappa, in some time interval from 0 to t, can be expressed in terms of the effective force with infrared cutoff equal to t. And the goal is to prove existence of the limit kappa goes to 0 of phi kappa. To this end, we will first prove a certain bounds for the effective force coefficients, which are uniform in both cutoffs, and which imply the absolute convergence of the series. And subsequently, we study existence of the limit kappa goes to 0. In this talk, I will concentrate on the proof of uniform bounds, which have the following schematic form. Note that the right-hand side of the bounds involves the maximum of the cutoffs, and the exponent rho depends on the indices I and m, and can be determined using dimensional analysis. In order to prove these bounds, we use induction that follows the recursive construction of the coefficients. We first prove the bound for the derivative of the coefficient with respect to the infrared cutoff. So in this step, we simply use the flow equation and the induction hypothesis. So this step is straightforward. It's also relatively easy to prove the bounds for the so-called irrelevant coefficients. So these are coefficients for which rho is strictly positive. So to prove this bound for irrelevant coefficients, we express the coefficient as an integral of its derivative. Subsequently, we obtain the following bound, and then we derive the right bound for the coefficient after plugging the bound for its derivative. Observe that in the last step, we crucially use the fact that rho is positive. This strategy does not work for the so-called relevant coefficients, for which rho is not positive. Fortunately, there are only finitely many such coefficients, and to prove bounds for these coefficients, we use a different strategy. We express the relevant effective force coefficients as a functions of certain simpler coefficients denoted by little f. So these coefficients depend only on one space-time point. And the finite collection of these coefficients is called the enhancement of the noise. It turns out that the bounds for the relevant effective force coefficients follow from certain bounds for the enhancement of the noise. And the bounds for the enhancement are proved using probabilistic tools. Elements of the enhancement of the noise are certain multilinear functionals of the noise that depend on the coefficients of the non-linearity. And we will prove that if the coefficients of the non-linearity satisfy certain constraints, then the bounds from the previous slide hold almost surely. And it turns out that to prove this statement, it is sufficient to prove certain bounds for cumulants of the elements of the enhancement of the noise. And we shall prove bounds which have the following schematic form. And the proof of these bounds is again by induction. To prove the induction hypothesis, we first prove a certain bound for the derivative of the cumulant with respect to the infrared cutoff. In this step, we are using a certain flow equation for cumulants, as well as the induction hypothesis. To prove the bound for the cumulant itself, we express the cumulant as the integral of its derivative. For the so-called irrelevant cumulants, that is the cumulants for which rho is strictly positive, it is sufficient to plug the bound for the derivative in order to obtain the correct bound for the cumulant. This strategy does not work for the relevant cumulants for which rho is not positive, because then the bound for the cumulant is not, for the derivative of the cumulant is not integrable in eta at 0 in the limit kappa goes to 0. Because of that, we have to use a different strategy to prove bounds for relevant cumulants. Fortunately, it turns out that the only relevant cumulants are expectations of one of the elements of the enhancement. And then by stationarity, such expectations are real numbers independent of the space-time point. And the idea is to impose certain renormalization conditions. So these renormalization conditions says that the expectation of the element of the enhancement with infrared cutoff equal to 1 is given to some constant that is fixed. And these constants that appear on the right-hand side of the renormalization conditions are effective parameters of the model. For example, effective mass or effective coupling constant. Now, using the normalization conditions, we can we have the following identity for the expectation of the element of the enhancement, and using this identity as well as the bound for the derivative of the expectation with respect to the infrared cutoff expressed obtained in the first step, we get the following bound for the expectation of the element of the enhancement. So observe that in this step, we crucially use the fact that now we integrate with a boundary condition at 1. So this allows us to avoid the non-integrable singularity at mu equal to 0. Let me finish the talk with a brief summary of the whole construction. So first, recall that the solution of the macroscopic equation can be expressed in terms of the effective force with infrared cutoff equal to t, evaluated at psi equal to 0. And the goal is to prove uniform bounds for phi kappa, as well as establish the limit kappa goes to 0. In this talk, I concentrated on the proof of the uniform bound. One can use a similar strategy to establish the existence of the limit. Okay, so in the first step, we impose certain constraints on the coefficients of the nonlinearity. Next, we prove certain bounds for cumulants of the enhancement of the noise using the strategy from the previous slide. Subsequently, we prove that there exists some random variable R, which has finite moments of all orders, such that the elements of the enhancement of the noise satisfy these bounds. Note that in this step, we use a variant of the Kolmogorov type argument. So this step is a bit similar to the proof that the Wiener process is almost surely almost one-half Hilbert continuous. Finally, we express the relevant effective force coefficients as functions of the enhancement of the noise. And this allows us to prove these bounds for the relevant effective force coefficients. The bounds for the irrelevant effective force coefficients follow then automatically from the flow equation. Finally, we express the solution in some time interval from 0 to t in terms of the effective force with infrared cutoff equal to t. And using the bounds for the effective force coefficients, we prove absolute convergence of this series, at least for times t, which are sufficiently small, depending on the random variable r. So this finishes the construction. Thank you for your attention.
Thank you, Pawel, for this talk. Are there any questions to Pawel from the audience?
Maybe I ask a question. You had this for this parameter sigma for your fractional Laplacian, you admitted values in the open interval from 2 to 3.
Yes.
And what is responsible for the upper bound? Or could you also go higher to?
Yeah, so it depends on the problem. Maybe I will go back to the theorem and so if you are only interested in the well-posedness result for this class of SPDEs, then sigma can be arbitrarily greater than 2.
Mm-hmm.
However, the case sigma greater than 4 is not interesting, because if sigma is greater than 4, then this equation is not singular. Mm-hmm. Yes, so it's very regular.
Mm-hmm. So you could do it, but it's not interesting, you say.
Yeah, but in the case of the universality result, this restriction sigma is between 2 and 3 is important. Because as sigma grows, the number of relevant terms also grow. And in particular, if sigma is greater or equal to 3, then the term phi to the 5th becomes relevant. And consequently, I mean, I can also apply my result to this case. However, then the result will be a bit different, because I will have to fix 3 relevant parameters, and the scaling limit will be parameterized by 3 numbers.
Mm-hmm.
So somehow the number of relevant terms depends on the choice of sigma, and also depends on the choice of delta. And so intuitively, so for example, if you consider the case of the equation with a standard Laplacian in 2 dimensions, mm-hmm. then you would not expect any universality in that case, because basically every polynomial is relevant.
Mm-hmm. Mm-hmm.
And in such case, roughly corresponds to this equation in 4 dimensions with sigma equal to 4. Mm-hmm. Mm-hmm. So then it's intuitively clear that as the sigma grows, the number of relevant terms should also grow.
Mm-hmm. Mm-hmm. I see. And just may I just join the question, because we are on this transparency. So for this polynomial, you can assume anything, any degree.
Yes, it can be
in size and gradient size and. And
I assume that the non-linearity is a local functional of psi respecting the symmetries, namely the sign flip symmetry and discrete rotation of the torus. And I assume that it only depends on psi, its gradient and second derivative. So this restriction to second derivative comes from the fact that this differential operator is of order less than 3. So I would like to have an equation that is semi-linear.
And could it also be non-polynomial, but somehow with convergence conditions on the coefficients, or?
Perhaps yes, but I did not study this case. However, this case was studied in the literature. In the case of models whose large scale behavior is governed by the KPZ equation or 5-4T model. So I think these papers studied more general qualities as well as yeah, I think also studied more general classes linearities.
Oh, thank you very much for the nice talk and for answering these questions.
Thanks.
I think there's another question by Roland.
Yes, thank you also for the nice talk. One point that I didn't quite get correctly is, so the results are hold for all times or for short times?
Short time. So
it's a usual short time story. You have a short time that depends on the noise, etc., right?
Yes, and I think
is it?
Yeah.
Oh, okay, yeah. So that was the first part of the question. And then is it conceivable in your framework to do something analogous to the Murat-Weber? So they get the long time existence from the equation by using the coercitivity of the phi-4 term in a way. Could you implement that in your scheme? Because I
would say presumably yes, but I didn't do it. So
that might be interesting, because as far as I remember, that uses more that, I mean, the special way the equations are subtracted, and then you see the phi to the 4 term or the phi cube term, I guess, still in the difference equation, etc. And I guess the way you organize things is a bit different, and seems of interest if you can also see the long time existence in this.
I think one could perhaps use the ideas from the paper by Monat and Weber. So in that paper, they are also studying a certain equation for the regular part of the solution for let's say object of this type.
Yeah.
So I presume.
But I imagine in your setting, so you have this effective force, and if you want to start, so I guess you have to solve the equation with effective force for a long time. I don't know if you have enough control on the effective force to do that or not. In any case, I don't know, but it seems an interesting question to me.
Yeah, it's definitely interesting, and I think it's perhaps possible to solve it in this framework, but I didn't do it.
Thank you. I think there's another question by Felix Otto. I can see. Anyway.
I don't know whether I'm next. Can you hear me?
Yes.
Okay. So I also had a little bit of a technical question, which perhaps goes a bit in the same direction as Ronald's question. So, so in this, I mean, in a certain sense, if I understand it correctly, you're using the flow equation twice. And perhaps the kind of more intricate part is in the stochastic estimates when you look at the enhanced noise and the cumulants. And there you have to work, of course, you have to work in, and you mentioned that, in the stationary setting.
Yes.
Whereas when you're interested in the original SPDE, you might want to consider, general initial data, which have nothing to do with the noise. So you're no longer in a stationary setting. So to me, it looks as if those were kind of, at least logically, quite separated uses of the flow equation. Is that correct?
Yes, that's correct. And the way from let's say this bound for cumulants to the bound for the effective force coefficients is a bit more complicated than I showed in the talk.
So then let me ask this question. So I'm trying to map that onto regularity structures. So this, I mean, the probabilistic part of the analysis is, in a certain sense, the construction and the estimate of a renormalized model. Mm-hmm. And then the deterministic part of the analysis is actually solving a specific equation with specific initial data. And in case of regularity structures, especially when you're kind of operating close to criticality, often, I mean, it's really important that you have what, in regularity structures is called the centered model. But that doesn't, I don't know, in which sense is kind of the centered model, which is enriched by polynomials, where you kind of put them into, in which sense is the centered model included in what you're doing in the probabilistic analysis?
Yeah, I don't think there is a good analogy here to the centered model.
So are you saying you're avoiding, you're able in kind of in the deterministic part of your analysis, so the one which you presented first, you're able to avoid kind of understanding what in regularity, I mean, in an implicit way, what in regularity structures would be called the centered model?
Yeah, I think so. The way I'm defining this enhancement of the noise is, I think, rather different than the definition in the theory of regularity structures. So I don't think there is a good analogy here, and I'm also not proving any regularity for elements of the enhancement. So these bounds that I'm proving for the enhancement quantify the behavior of the elements of the enhancement at some scale mu that also appears here. So essentially, I'm only controlling the behavior of this object with infrared cutoff mu at scale mu.
Mm-hmm.
That I mean that I'm convolving this object with some kernel at scale mu.
Mm-hmm. Mm-hmm.
So I am not really proving anything about regularity of this object. I'm proving certain bounds which turn out to be useful in the deterministic analysis.
Mm-hmm.
So because of that, I do not need any positive regularization.
Mm-hmm. Okay, thank you.
Any other questions to Pawel? If not, then I may be allowed to ask a question about the absolute convergence of the effective action. Is that due to the super-renormalizability in the end?
Yeah, so super-renormalizability is definitely crucial in this whole framework. However, this convergence is due to the short time. So the
okay.
parameter here is time, and I have to choose sufficiently small time interval to have convergence.
Yeah. Okay. All right. Any further questions to Pawel? Browse through. Don't see a hand. If not, then thanks very much again to you to Poznan, and thanks to all others in the United Kingdom and many other places for tuning in, and see you next month, I suppose. Bye.
Thanks. Bye.
Bye.